Okay, so I've just recapped what we looked at before. The exact solution, x hat, is the approximate solution, r is the residual, and it has these two ideas. And ax equals b is the system we're trying to solve. So anyway, we defined something called the Euclidean norm here, which is also known as the L2 norm. And you can see here it's just the way it's done is if I show you a quick example of it, what we're saying is if you have, say, 3, 4, then the norm, and this is x, for instance, then the norm of x, according to the norm of x, this one, is equal to square root of 3 squared plus 4 squared. 9 plus 16 is 25, so it's equal to 5. Okay, and the infinity norm, or maximum norm, sorry, okay, no, the infinity norm or maximum norm is, in fact, the largest number that you see here. So, sorry, I didn't define that here. That's actually equal to the maximum absolute value of the xi's, okay, for I between 1 to n, okay. That means for the entire vector. So you look at all the rows, what's the largest value? It's 4, so it's equal to 4 in this case. And we look at the absolute value. So anyway, so this shows us that the maximum norm is in fact, in this case, 4, and the Euclidean norm is in fact 5 in this case. Okay. So now, with those two defined, we'll also define something called the maximum row sum norm. Okay, max row sum norm, which is for matrices, because these two are for in fact vectors. So if for a matrix A, okay, matrix A, the norm of the matrix A is equal to, in fact, the definition is it's equal to the max. This is the maximum row sum norm. So what it's actually saying is, best if I show you a quick example here. So if we have 1, 2, 3, 4, 5, 6, 7, 7, 8, for instance, then what this is telling me is that, look, okay, let's put in some negative numbers in here. So what it's saying is 1 plus 2 is 3 and 3 is 6. 4 and 5 is 9 and 6 is 15. So I'm ignoring the negative signs. 7 and 7, 14, and 8, 14 and 8 is 22. So what's the largest number here? 22. So if this was A, okay, this is A, then norm of A, or the maximum row sum norm of A, is actually 22, the number 22. So this is just an example to quickly demonstrate how this actually works. Sorry, maximum row sum norm also now defined. Now let's see if we can move on to calculate what the condition number. Okay, so now we're ready to move on. Let's have a look at just looking at collecting all the information we need to define this condition number. So what I've done is I've got two properties here that I need you to look at. They're the same property, in fact. This, as you can see, the matrix AX, norm of that is less than or equal to the norm of A times the norm of X. So you can, if you separate these two out into their individual norms, then you'll always find this inequality present. Same way for any two matrices AB, where multiplication is possible, of course, otherwise there's no point. So AB of appropriate size such that multiplication is possible, then this is less than or equal to, of course, the individual norms. So this is an important property. We will now move on to derive the condition number. Okay, so let's start. I'm going to keep this here in a little box here so the information is there in case you need to look at it. We know that AX hat, okay, equals B. That's the exact solution, right? From this, we also know we can get that, well, this implies from this that X hat is in fact A inverse times B. That's simple, very simple. If, of course, assuming the inverse exists. Now in this we are assuming the inverse, of course, exists. This is A is non-singular. The other thing we also can look at is that A times epsilon, okay, is equal to R. You'll see that here. We already have that. So A epsilon is equal to R, which further implies that if I want to say what is epsilon, then epsilon is in fact A inverse times R. Okay. Now, if I apply these norm properties, I'm going to use these norm properties and apply it to these ideas, these four ideas that you see here. Fine. So if you look at the first of these, for instance, clearly, if I say what is the norm of B, then that's equal to the norm of AX hat, clearly. Simple. Just take the norm of both sides. B is equal to this. Now, according to this property here, this means this is less than, so this means that this is less than or equal to, if I separate these out, I end up with this, okay? Which means that, in other words, B, the norm of B, is less than or equal to the norm of A times x hat, okay? Put a little square on that, all right? Let's call that equation, well, let's not call it anything for now. Okay, so we've got that. Now, in a similar way, if I go to the other relationship here, which is x equals A inverse B, then clearly x hat, the norm of that, okay, and I'm going to this equation now, this relationship, then x hat is equal to, of course, A inverse times B, norm of that, which is less than or equal to the norm of A inverse times the norm of B. Should be simple enough, which means essentially that the norm of x is less than or equal to the norm of A inverse times the norm of B. Let me put a square on that as well. So easy enough. I hope you can see where that's coming from. Let's go to the next set of equations, the next two equations. I know they're coming from the same one, but that's not the point. The point is, you see this one now here. Let's look at what is the norm of R from this. Well, the norm of R is equal to the norm of A times epsilon, which is less than or equal to the norm of A times the norm of epsilon, which means essentially that R is less than or equal to norm of A times norm of epsilon. Let's put a little square on that. So these are three important results. That leaves us with the last one, which is this one here. And from this, what we can get is that norm of epsilon, okay, one more time, is equal to the norm of A inverse times the norm of R, which is less than or equal to the norm of A inverse times the norm of R. Okay, and that means basically that it means that a little box on that. Now, so we've got these four relationships, and what we want to do with these four relationships is try to combine them to look at what's the relative error. So what I want to do actually at the end of this is I want to find what is epsilon divided by the exact. So this is the relative error. Okay, this is the relative error. Okay, now in order for me to work this out, I'm going to go slowly first, very slowly. So if I look at epsilon, let's look at epsilon for a moment. So what we see here is epsilon is less than or equal to this, which means I'm just going to write that down here. So epsilon is less than or equal to A inverse R. Okay, 1. Now, if I go back and I look at this other epsilon relationship here, from this I can say, well, this implies that epsilon, in fact, okay, is greater than or equal to R over A. Simple, right? Just send it to the other side, which means I've got my lower bound for epsilon. It's between R, it's just R over A. So now I've got a very simple, straightforward upper and lower bound on the epsilon. Now, in a similar way, if I now try to calculate, look at 1 over x. If I try to look at 1 over x, okay? Now, this requires a little bit of manipulation in the sense that let's go to where do we see x hat? Well, we see it here and we see it here. Okay, so this one tells me that x hat is less than or equal to A inverse B, which means that 1 over x hat, okay, 1 over x hat is going to be what? Well, let's have a look. So from here, 1 over x hat, if I turn it upside down, okay, 1 over x hat. Okay, now if I turn it upside down, the inequality will of course flip, and it will change this way. Okay, it'll be the opposite, and of course these will all go in the denominator. So this gives me a lower bound. This means that I can say, well, okay, wait. This means that 1 over x is bigger than 1 over a inverse times b. That's simple, right? Now, in a similar way, if I go back up here, over here, well, I can see that if I calculate what is 1 over x in this. In order to do that, let me go a couple of steps. So x hat from this, okay, is greater than or equal to b over a. Simple. Now, let's get some more space here. Okay. So it's b over a, which means if I turn it upside down, 1 over x less than or equal to a over b. Simple. Which means I have my upper bound here for this. Okay, so now I've got these two interesting results. I've got an upper and lower bound on epsilon and 1 over x. Now if I multiply these two together, so in order for now, if I want to now calculate my final result, which is this, then what is the upper and lower bound on this? Well, it's simple. Just take this here, you take this here and multiply it by this, because we multiplied these two, so now we'll multiply these two. So that's going to give me basically r, okay, over a, r over a into 1 over a inverse b. Okay, and if I take these two and multiply them, then I'm going to get here a inverse r all, wait. I'll take it really slow. So I'm just going to multiply them. So I'm going to have this multiplied by a over b. Okay, simple, straightforward. So if I rearrange these a little bit, so what happens is, this is where it is, of course. But here, what I want to do is I want to take these two and keep them together, okay, and have 1 over. I want these two to be together, okay, and I can do the same thing on the other side. So I get this times the a norm multiplied by r over b. So now I've got an upper and lower bound on, in fact, the relative error. Remember, this is a very interesting result. It gives us an upper and lower bound on the relative error. Now we define k kappa of a at this point, and that's called the condition number. Okay, this is called condition number of a. So this is the Greek letter kappa, and it's basically this. So that means that our further this becomes, and just let me show you what, and replace epsilon here with what it's what it is by definition, which is x hat minus x approximation, the norm of that, divided by the norm of x, the hat, which is the exact. So that's equal to 1 over kappa a r over b, and you've got the same r over b on this side. Okay, the norms, and you've multiplied by kappa a as well. So now we've got basically this very interesting result. Now, from this, let's try to analyze what kind of condition number gives us what kind of relative error, or what can we actually deduce from this result. Now, if we in fact look at the condition number, okay, so if we look at this A inverse A, okay, now if we reverse the property which we used before, let me show you very quickly. Oh, sorry. Let me show you very quickly what property I'm talking about. I'm talking about this property here. So I'm talking about this property here, this one, okay? AX is less than or equal to norm of A, norm of X. Now, I have this side, which means that if I want to combine them, I'm going to reverse this. So that means I'll end up with, sorry. So I'm going to end up with, this is in fact greater than or equal to AA inverse. Now there's a reason I'm doing this. Well, that is the norm of the identity. The norm of the identity is 1. So that means that kappa A is greater than or equal to 1. Okay? So that means that kappa is always greater than or equal to 1. Now, that's a very important and interesting result. If kappa A in fact is equal to 1, this implies that we can exactly compute, in fact, the relative error. Okay, relative error is equal to, in fact, in this case, over B. Okay, that's an important result. Okay, that's an important result. So, on the other hand, we also note that if kappa A is small, okay, then a small residual implies a small error, which is good news, which means we have confidence in the residual. So if it's a small residual and the condition number is small, we can say that it means the error will be small. However, for large condition number, it is possible that the residual can be small, like in our example, and the error will be large. So for large condition number, we say that the matrix is ill-conditioned. It is ill-conditioned, and then if it's an ill-conditioned matrix, it is possible that the residual can be small, but it doesn't indicate a small error. So now, if we go back to the example we looked at earlier. So now, if we look at this was the system AX equals B we looked at before. Now, in this case, you can clearly see that this is 0.2161. You can see this is the inverse here. I've got the inverse here for you, and you can see that if I were to calculate now the condition number, okay, that's going to be equal to, in fact, it's okay, let me just calculate it piece by piece for a second. So it's equal to, of course, norm of A times the norm of A inverse. Now, if we calculate that norm of A here, let's do that. So norm of A is going to be the max of, it's the max of, that's how it works out. So A is that. And similarly, if we go to A inverse, so that's going to be, so it's equal to that. So these two then give us the condition number. So when we multiply them, this is approximately 3.27 into 10 to the power 8. So now you can see that's a very large condition number. So the matrix, so A is ill-conditioned. So we say A is ill-conditioned. Now, ill-conditioning is a property of the given system of equations. Now, it may not be possible for us to cope with it, in particular when certain precision is used. In this example that we've looked at, double precision, in fact, could be used, and it can overcome this ill conditioning property of this matrix. However, if, for instance, the condition number is to the order of 10 to the 20, for instance, then it's essentially insoluble. This is just to give you a rough estimate, because it's very difficult to get exact values of what kind of condition number has what in fact result. Ill conditioning is not something necessarily that cannot be overcome, but it can, in fact, in certain cases, for kappa being say 10 to the 20, it's the problem is is in fact insoluble. Now it may be very important. Now you can clearly see that it may be very important to know the magnitude or the condition number actually, and it's not necessarily easy to calculate the inverse of a matrix. So in the next video, we're going to look at how we can estimate the condition number.